Hello everyone and welcome to the new episode of our series of solving LeetCode Daily challenges. And today we are going to solve a problem called maximum number of events that can be attended to, which has a hard difficulty, which is great because on this channel we love hard problems and we love making them easy for you guys. So without further ado, let's move to the problem statement. We are given an array of events, and each event is defined by its start day, end day, and value. We are also given an integer k, which represents the maximum number of events that we can attend. We can attend only one event at a time. If we choose to attend an event, we need to attend the entire event, and we cannot attend two events where one of them starts and the other ends on the same day. And we need to return the maximum sum of values, so this value, of values that you can receive by attending events. Okay, let's look at the constraints. So the most important constraint here is that k times event length is less than or equal to a million. Okay, because this right away it just sends our mind in the right direction. If we have such a specific constraint, it's quite likely that this value of k times event length will be present in our complexity in one way or the other. And the other constraints are also important, but they are less important. Okay, so let's proceed to the solution of this problem. So whenever I see such optimization problems, I always think, is it possible to implement dynamic programming solution for such a problem? And in this case, it is possible. So first of all, let's sort events by their start day, which is basically an order in which we can attend them. So for example, if we have a list of events like this, their sorted order looks like this. So this event starts at day 1, ends at day 3, and has a value of 4, and so on. Okay, and to solve this problem, we are going to use a recursive DP, because 95% of the time when I implement dynamic programming, I usually do it in a recursive way, and I will show you exactly how I did it for this problem. So let's define our recursive function. We will call it solve, and it will take exactly two parameters. The first one is an index, which is an index of event in this sorted array, and the other is events left, which basically shows how many events can we still attend. Okay, so first of all, let's consider a couple of edge scenarios, the basis of our recursion. So if we have no events left, so if events left is equal to 0, then we cannot attend anything, and we should return 0. If our index is equal to event size, this means that we have already looked through all of the events and we cannot attend anything else, so we should also return 0. Okay, now the next condition is basically critical to every recursive DP, and it tells us if we have already been in state defined by this index and events left, we should return the cached value. So whenever we have processed some state, we put the result in cache, and the next time we encounter the state, we just return the cached value. And I will show you how it works on practice quite soon. Okay, suppose that none of these conditions actually apply, then we have to implement our recursive transitions. So suppose we are looking at some event and we have a certain amount of events left to attend. So the first option that we have is to just skip this event, do not attend it. And this basically brings us to the state of solve from index plus 1. Basically it means that we are going to look at the next event and either choose or decline this event. And our events left does not choose. Or we can attend the next event. We will receive a reward for it, which is value of index. And then we will transition to the next state of our recursion. which is next possible event, and I will talk about it in a second, and events left -1, because we have just used one event. So what's next possible event? Suppose we have such event, and we decided that, okay, we are going to attend this event. It has a start date and an end date, right? So the next event that we can take should start at the day that is bigger than the end day of our current event. And this next possible event basically tells us the smallest possible index in this sorted array of events of an event that we can actually attend if we take the current event. So basically, yeah, we want to find the next event that we can attend after this event. I hope I made this clear. So, okay, let's look at this recursion. It has exactly a big O of n times k states, where n is the event's length. And we remember from our constraints that n times k is less than or equal to 1,000,000, which is good. And we have recursive transitions that work in constant complexity, except of this statement that we don't know how fast does it work. How fast can we find this next possible event? But if we assume that we can find it really quick, let's say in constant complexity, once again, then our current solution is big O, the complexity of our current solution is big O of n times logarithm of n, because we need to sort our events by their start date, plus n times k, which is great, which fits all of our limitations. However, we do not know how to find this next possible event quickly. So let's proceed and figure it out. So how do we find the next possible event? Before we launch our dynamic programming, for every end day, let's find the first event with start date bigger than given end day. And to do that, we are going to use 2 pointers. Okay, so let's once again consider our example. Here it is. I have put it here as well, and I called it sorted events. And let's also create another array. We will call it sorted end days. And here we will just put all of the end days of all of the events and sort them in increasing order. And our goal is for each of these end days find the first index in this array of sorted events such that the start day of this event is strictly bigger than our current value of end day. And I'm going to show you an example, and I hope it will get much clearer. And we have a map. I will call it next event by end day, and it will show us exactly that. Okay, so we are going to use 2 pointers. Some people call this technique sliding window, but I think that sliding window is a completely different technique, because yeah, I don't see a window here. In actual sliding window, there is a window. So yeah, we are going to call this 2 pointers. And we have a pointer that points to an entry in this sorted end days array, and we have a pointer that points to an entry in the sorted events array. Okay, so suppose we are looking at some event. Let's look at the corresponding end day. Does this end day come before our current start day? No, it doesn't. Okay, let's move to the next sorted events entry. Okay, does this end day go before this start day? No, it doesn't. Okay, so let's consider the next event. Does this end day comes before this start day? Yes, it does. Let's add an entry to our map that will tell us that for an end day of 3, the first possible index of next event is 2, because this event has index 0, this one has index 1, and this one has index 2. And this will be the first entry in our map. Okay, in this case, we move our second pointer. So we actually move a pointer in the sorted end days array. And now we are taking a look again. Does this end day comes before this start day? Yes, it does. Okay, so let's add an entry of 4.2 to our map. Okay, and let's take a look at this final end day. Does this end day comes before this start day? No, it doesn't. Okay, and basically we are done. We have looked through all sorted end days and we have looked through all sorted events. But also for our convenience, we will put an extra entry to our map, which will tell us that for an end day of 7, you have to go to the end of the array to find the next possible event, which technically means that if we have attended the event that ends at day 7, then there is no more events for us to attend. And yeah, we have put here an value of sorted events.size just for our convenience to make our recursion easier. Okay, and that's pretty much it. And these 2 pointers will work really fast because yeah, of course we are going to need to sort our values, so we are going to have a complexity of big O of n times logarithm of n, but after that we are going to only implement big O of n operations, so the total complexity of this procedure is big O of n times logarithm of n. Cool, so let's look at how I implemented this solution, because yeah, now we have all of the pieces in place. We know how to find this next possible event really quick based on this map, and we have calculated this map based on 2 pointers, and everything looks great. So let's look at the code. So first of all, I have created a simple class called event, which will represent an event, and it has 3 fields: start day, end day, value, and the constructor. I've made these fields public just to make the code look simpler, but of course you gotta like make them private, implement getters, stuff like that. But in here, for our convenience, let's have all of the fields public. And here is our main method. First of all, we create this list of events which will be sorted by start day, and to do that we just create an event for each of the entry of our array of events and basically sort them by their start day, so nothing hard in here. Then we create a list of all possible end days, once again sorted in increasing order, so nothing hard in here. Then we will use 2 pointers technique to calculate our next event by end day map, and I'm going to do it in a separate method called next event by end day. Let's take a look at it. And basically it's just 2 pointers. We have this map, this resulting map. We have our pointer number 1. We are going to iterate through the second pointer in our for loop, and then we are going to have a while loop, and we are going to check while our current end day is smaller than the start day of our current events sorted in increasing order. We'll just put an entry to the map and increase the index in this first array of sorted end days. Okay, and in the end we are going to do this thing that I said we are going to do for our convenience. If some end day is bigger than all of the possible start days, then for this end days we are just going to put the value of events.size in our map. And that's pretty much it. So now we have this map that will help us do our recursive transitions. We are going to prepare our cache, and to do that I'm going to create a 2-dimensional array with the size of n times chi plus 1, and I'm going to fill it with -1s. So quite easy. Because -1 basically represents the state which we did not attend, because the results of our recursion will definitely be non-negative because all of the values are positive. So we can just assume that if our cache says that the result for this state is negative, this means that we have never actually attended this state. Okay, and in the end, I'm simply returning the recursive call from 0 and k, which basically means that currently we are taking a look at the first event or event with index 0, and we have k events left. So let's take a look at the recursion and how it's implemented. So at first we have our base cases. If events left is equal to 0, we return 0. If we have looked through all of the events, we return 0. If we have already been in our current state, we return the value of this current state. And yeah, that's good. We have already processed all of our base cases. Let's look at our transitions. Our first transition is to skip this event and move to state index +1, so next event, and the same number of events left. And our second transition is to get event.value points to our result and add it to the solve of moving to the next state based on this next event by end day map. So we know what's the next event that we can theoretically attend after this one. And we will decrease the number of events left. Okay, so we have chosen the maximum between those two results. We have put this result into cache, and now we return it. And that's pretty much it. That's it for this problem. Okay, guys, so as I said, the complexity for this solution is big O of n times logarithm of n, because we do some sorting in here, plus big O of n times k, because that's the complexity of our dynamic programming. And since n times k is small enough, that's good enough for us. Okay, so thank you guys for your attention. I hope I made this problem more or less clear for you. If you like my content, please press like, subscribe, leave some comments. I will try to answer all of them. And have a very, very good day. Bye-bye.